important in these things. So earlier we have seen the conduction through the walls and exterior walls, roofs, glass. Secondly, conduction through interior walls, ceilings and floors. Radiation through the glass, lighting, people's equipment, and heat from infiltration of outside air through the openings. See here. So for all these things, there are some formulas we will try to understand. See here. Let me show you the things here. So here there is a formula here. See here there is a formula. Cooling load temperature difference is equal to CLTD plus LM plus 78 minus TR plus TA minus 75. This is formula, okay. So this formula is generated based on this indoor temperature as well as the design day what is considered here. This is a little bit tricky here. So you can see the data book and ASHRAE tables for few things, because these are the parameters required for finding out the cooling load temperature differences for this particular heat gains, conduction through the exterior structure of the roof and all. So TA is T0 minus dr by 2. You can see here TA is the average temperature outside the design day and TR is the room temperature. So T0 is outside design temperature of the bulb. So the dr is daily mean temperature ranges, is also found in the ASHRAE tables. Secondly, conduction through the internal structure. See here the conduction through interior structure. So Q, that is a heat gain to the partition, floor or ceiling, that is expressed in BTU per hour. So Q is equal to UATD. Q, I already told you. U is overall heat transfer coefficient for partition of floor or ceiling, that is expressed in BTU per hour. I told this is the temperature difference TD. So this is how with this formula, if you know U value you can take from the data book. Area, you know the area of slab or the wall you are going to consider. T is the temperature difference for outside and inside temperatures. You can match it and you can get the Q value. See guys, you can understand the Q value is BTU per hour. Okay. Coming to third one, solar radiation through the glass. So whenever there is sunlight passing through the glass, so the radiation, sun radiation is affecting the glass, and internally it is also heating the space. Here you can see the CLTD corrected glass is equal to CLTD plus 78 minus TR plus TM minus 85. So whatever the things you got, the CLTD corrected glass, you have to put in the this area, because conductive of the glass, Q conductive is equal to UA CLTD. So these obtained value you have to put here. So this is for the calculation of solar radiation through the glass. So other things you can get from the data book. See here, the solar transmission heat gains through window glazed surfaces. So Q solar, glass solar is equal to A into SC into SL. So A is area of a glass, SC is shaded coefficient, it is solar cooling load. Solar cooling load you can take from the tables, and SC is uh, cooling load factor and area. So you can take this as 1 and you can take these value from the tables, and area of glass you can measure area of glass. You can get the solar transmission as well as the heat gains through the window glazed surfaces. Glass cooling load for radiation, the Q is equal to A into area, that is shaded coefficient, into SHGF, solar heat gain factor from tables, and CLF. These are cooling load you can take from tables again. You can take down the values, you can check, you can find out from the data book and all. Okay. So we have seen little bit about the external heat gains, are just like getting the internal partition walls getting heated, floor is getting heated, as well as the roof, the concrete slab is getting heated, and radiation through the glass, solar transmission, these kind of things. So these all things you will be getting the Q value. So what is the Q value? Try to totally add it and put in somewhere. It's all comes under the sensible load. So just now we have seen all the external heat gains. Now we are seeing the internal heat gains. Means internal heat gains, who and all contributing sensible as well as latent heat. Only sensible and sensible as well as latent. So inside the room, guys, we can understand, inside the space where we stay, people will be there, occupants will be there. See, people will try to breathe, inhale, exhale the air. So when they are putting the air outside, exhaling, so some amount of moisture is also being added to the space. Do you agree, I guess? And people also to start exhibiting or contributing some of the heat emitted from the body, that is called sensible heat. So sensible heat and latent heat both are being given by the peoples. So you have to consider both the things here. Coming to lighting, so lighting only sensible because it will generate only heat. Light cannot generate any humidity. That's why the sensibility is there here. Equipment. Equipment can give sensible as well as latent. Why I am telling you this? Suppose if you take an iron box only gives the sensible heat. Whereas if you take a coffee maker or a milk boiler kind of thing, it will generate heat as well as humidity, because humidity in the form of what is the steam. Now we will see the formulas for each and everything and how to calculate. For people, since sensible and latent heat gain are there, you try to take these all values from the ASHRAE handbook. So QS is equal to small qs into N into CLF. CLF is a cooling load factor, it is an adjustments, and N is number of people inside. Q is sensible heat load. So sensible heat you can take from the ASHRAE data book. So sensible heat of persons, people. So QL is equal to QL into N. So same wise, QL is equal to QL into N. This is the number of people, and QL is latent heat of the people. So you will be getting both the things here, both sensible as well as latent. So CLF as of now you can take 1, because these are the cooling load factors are just an adjustments only. Coming to lighting. In lighting, we need to understand the concept like electrical ballast. Okay, this is a device intended to limit the amount of current passing through the circuit, so resisting. Okay, so an incandescent light bulb which produces light through filaments, and thus gases present in the bulb start excitation. So it will be converted into the visible light. So there are the fluorescent lamps also. So mercury coated inside the glass. You can see here. So here you can see. So we are discussing here. See here the fluorescent lamps. So the formula is Q is equal to 3.4 into W into BF into cooling load factor. So 3.4, if you are not multiplying with 3.4, this Q value will not be coming in BTU per hour. So these are the constant factors we are trying to multiply so that the Q value will be not in watts, it will be in BTU per hour. So Q is equal to 3.4 into W, the watts, into number of watts, number of bulbs into watts of each bulb into ballast factor. The ballast factor you can take as 1 generally. So you can see, so typical ballast factor is 1.25 fluorescence, and for incandescence you can take 1. So I think you understood this one. So from there you can get the BTU value. Coming to equipments, we can have equipments which generate sensible heat as well as latent heat. So first one is, see, suppose if you are having a motor, so you can try to get the technical details from the motors and other kind of equipment, how much it is going to generate basically. Suppose a monitor, so a 12-inch monitor, 15-inch monitor, 21-inch monitor kind of thing, how much heat is generated by monitor, you can take all the details from the vendor, you can say. Guys, I am telling you one more thing. Often you try to have an association with the professional group in the LinkedIn and all, and you try to comment what are the things we are discussing. It is not the way of discussing just like a normal non-technical way, putting good, bad, nice. No, you have to talk in a technical manner so that the whomever you are trying to discuss, it will exhibit your capability mainly, or your capacity with your enthusiasm of interacting with the online course here, as well as you will have an good impression on the peers who are looking in this discussion.